So Edward Pickering hires William N. Fleming to do spectral analysis, but she does a lot more than just looking at photographs. She comes up with a system of ranking the spectra by the amount of hydrogen in the spectrum and giving a letters A through O to analyze this. So then William Pickering hires a bunch of other women to work for him. One of these that he hired was Annie Cannon. Now, Annie Cannon looks at William N. Fleming's work and says, well, there's only some of these letters that have stars, A, B, F, G, K, M, and O. So what she does is she rearranges them in order of temperature, O, B, A, F, G, K, M, in which the hot stars are to the left and the less hot stars are to the right. Now, I don't want to say exactly cool, though I wrote that down, because they're still red hot, because these are red stars. So this became the new system here, OBAFGKM. The A stars have the most obvious hydrogen in them, but that doesn't mean they have the most hydrogen in the star. It just simply means they have the most obvious hydrogen in the spectrum because they're the right temperature for the electrons to primarily be in the second energy level. Okay, this is what became known as the Harvard classification system. So Annie Cannon comes along here, rearranges it, and then she expands it one step further. Each individual letter is subdivided into 10 subtypes. So B becomes B0, B1, B2, B3, so forth down to B9. A's became A0, A1, A2, A3 down to A9, and so forth. And so each one of these was subdivided into several different sub-branches. Okay, and so that gives you this wide range of different spectral characteristics. At this point, I kind of like to point out that Sirius, the dog star, is not a K9. The Sirius is actually an A1. Okay, so it's a hot star. The sun, however, if we're going to look at the sun is a G2 star. So that's kind of in the middle of that spectral range, OBAFGKM. And so the sun's kind of mid-range in temperature between the hottest and the coolest. Now, next question is, suppose we have a bunch of stars similar to the sun, and I want to know which one's most like the sun. How would you figure that out? So let's imagine we got the sun, which is a G2, and I have several other stars out here. I have a star A here, and star A is an F8, okay, and then I have star B, and star B is going to be a G7. And I want to know which one's closer to the sun. Well, your first thing is, aha, that's a G, so that's got to be closer to the sun. Well, let's think about this. The sun is a G2. So what's the next closest to a G2? Well, that would be a G1 or a G3. Next closest is a G0 or a G4. Next closest is an F9 or a G5. The next one is an F8 or a G6. So that means the F8 is actually closer to a G2 than a G7 would be. And so that's how you'd figure out which of these stars is actually closer in temperature to something. Okay. So back to Annie Cannon here, OBAFGKM. She actually categorized close to 1 million stars in her lifetime. In fact, they say every observatory has to have a good ghost story, and so they say that her ghost still wanders around the Harvard College Observatory looking for stars to classify. And then there she is sitting here looking at a glass plate classifying stars in this photograph. Now the thing is, she was so good, so spectacular in what she did, totally revolutionized our entire understanding of stars, that they actually published her work under her name. Edward Pickering, told the publishers, there's no way you can't publish this, and so they ended up publishing it under her name, so she actually got the credit she deserved for it. They published the Henry Draper catalog. Henry Draper, remember, took the first spectrum of a star, photographed it, and the endowment that his wife gave to the observatory funded all this work. And so when they published her Annie Cannon's star catalog, it became known as the Henry Draper catalog of stellar spectroscopy. So when you hear about an HD number of a star, it's in her catalog. She was even awarded a couple of very prestigious prizes. She was the second woman ever admitted into the American Academy of Sciences. Ironically, the first woman admitted to the American Academy of Sciences was none other than Maria Mitchell, who actually started the whole thing of American women in astronomy. And then Annie Cannon here also became the very first woman admitted into the faculty of Harvard University, the very first woman professor at the university. So when you're studying the spectrum of stars, again, OBAF-GKM, from her way of doing it, A stars had the most obvious hydrogen spectra, but there are other spectral lines here that show up in other stars. Now, there's a mnemonic that's often given to remember the order of the spectral types. O be a fine girl, kiss me, or O be a fine guy, kiss me. And so that's how you remember the order, OBAF-GKM, from hottest to coolest. Okay, so back to our table of data here that we've seen a couple times. And it's like, okay, so the spectral type column, don't not worry about those Roman numerals. We'll talk about those later. The spectral type column gives you which stars are going to be what temperatures. So the question is, what's the hottest star on that list? Well, what's the hottest spectral type? O. So you look, are there any O's on the list? No, there's no O's. So the next question is, okay, what's the next hottest spectral type? And that's going to be B. Are there any B's? And the answer is yes, there are B's on the spectrum on here. There's one right here, there's two right there. So which of those B's is the hottest? That's going to be B0. So that's the hottest star on that list. And so that would be the star Epsilon Persei. So the next question is, what's the coolest star on the list? Well, the coolest spectral type is an M. And so are there any M's? And yes, there are several M's. There's one up here, there's one right there, there's one right there. So there's 3 M's. So which is the coolest? Well, there's a tie. That's an M4, and that's an M4. So these two stars are tied for being the coolest on that list. So the next question is, which of those stars is closest to the sun in temperature? So what's the sun? The sun is a G2. Are there any G2s on here? There are no G2s. So what's the closest that's here to G2? That'd be the next closest, G1 or a G3. We do have a G1. So Epsilon Leo is going to be the star most like the sun in temperature. So that's how you read that list. Okay. So you can look at this, and you can look at any two stars. Any two stars. So we can pick this star and this star right here. So Procyon and Lambda Velorum, and say which one's hotter and which one's cooler. Well, Procyon is F5, Lambda Velorum is K4. So an F5 is hotter than a K4. F is hotter than K. What about the next two stars? So the next two stars on the list here are Lambda Velorum and Psi Ursa Majoris. Which of those is hotter? Well, Psi Ursa Majoris is a K1, and Lambda Velorum is a K4. And so K1 is hotter than K4. Again, this is basically just reading that list of stars right there. Another way of looking at this is looking at the spectral lines, or what we call intensity trace. And so this is what astronomers mostly do, is they look at intensity trace. And so that would be a graph, and the graph would show you the intensity and the wavelength, and these dips here correspond to those dark lines that we see up there. So this would be, if we were doing in person, one of the lab exercises we do actually looks at the spectra of stars, and you compare an unknown star to a known spectral type and try to match that up to figure out what spectral type the star is going to be. And again, there are tables and charts. This is from your book, which shows you which spectral which spectral lines tend to be dominant in each one. So what you would do is, if you see the hydrogen spectrum, you know it's a star that's one of these right here. If you see a sodium spectral line, you know it's going to be one of these cool stars down here. If you see some of these other spectral lines, it's kind of like dead giveaways, an M star, an O star, or B star, or something, because you only see those spectral lines in certain kinds of stars. Okay. Your book has kind of a graphic right here that shows you which spectral lines are most obvious in which kind of star. And so astronomers get very adept at reading spectral lines and looking at the spectrum of stars to figure out what type of spectral lines are there. They're like fingerprints. Each set of spectral lines is unique to a particular element, and so these fingerprints are what you use to figure out the composition, and also we now realize that's also going to tell us the temperature of a star. Well, with better telescopes, astronomers realized that M was not the dimmest star visible. There are dimmer stars. There are some stars that are even cooler. And so they added L and T. L is like a super cool star. In fact, some of the L's might not even be stars. T's are probably not stars at all. They are what we call brown dwarfs, which are failed stars, things that form like a star, but they don't ignite to become a star, and they just gradually get cooler and cooler and cooler. In 2013, they added something else that is actually between planet and star in size. So these are spectral type Y. There's only a handful of them that we've found because they're super dim and super faint. So you got to come with new mnemonic for O, B, A, F, G, K, M, L, T, Y. And so don't know what you'd call that, but there ought to be some new mnemonic for that. Okay, again, from your book, this is a list of the different kinds of spectral types that are available, example of stars that are in that spectral type, and then what kind of possible spectral lines you might see. So this is all related to this Harvard spectral classification system that Annie Cannon came up with.